Okay, welcome to really the last day of new material for calculus. Day 14, area between two curves. Okay, we've done area under curves already by doing integrals or our anti-derivatives. And we knew that what we did before, we did basically the fundamental theorem of calculus. That between points A and B, the area under the curve and between the x-axis was the integral from a to b of f of x, and we did upper minus lower. And we found this area that is shaded here in pencil, and we did our integral or our anti-differentiation. Okay, what about if we did it with two curves and one of them wasn't the x-axis? So the idea is, it's the same idea. Because what we really did was, this was the area between two curves, where the upper curve is f of x, and the lower curve is really the x-axis, which is y equals 0. So what we really did was the upper curve minus the lower curve. It just happened that the lower curve equation is equal to 0. So what we're going to do now is we're going to look at really two distinct curves, a line, a parabola, or some other things. And what we're going to do is this, change to red, that the area between two curves between points x equals a and x equals b is always the upper curve minus the lower curve, and where maybe f is the upper curve and g is the lower curve between the limits a and b. Area will always be positive because we're always doing the upper minus the lower. It does matter the way you do things. Okay, we're going to find the area of this little shaded region, this little sliver. That is, the upper curve is the square root of x. The lower curve is just the diagonal line x. And obviously they intersect here and here. So from 0 to 1. So it's going to be from 0 to 1. The upper curve is the square root of x minus the lower curve x dx, or better yet, they really cannot take the integral with the square root of x to the 1/2 minus x dx. We've done a lot of these lately, taking integrals. Equals 2/3 x to the 3/2 minus 1/2 x squared. Evaluate it from 0 to 1. Equals 2/3 times 1 to the 3/2 minus 1/2 of 1 squared. All minus, oh, I love plugging in 0. That is just 0. When I plug it in, I get 2/3 minus 1/2, which is 4, 6 minus 3, 6. This little sliver, that little area, is equal to 1, 6. Top curve minus, upper curve minus lower curve. Okay, our next problem, we're trying to find this shaded region again. Kind of given to you that the upper and lower limits for the integral are going to be 1 and 3. You can see these, that it's stuck between these vertical lines. So it's an integral of 1 to 3. My upper curve is the f function, which is going to be x squared plus x minus 4, minus the lower curve, which is a very similar function, x squared minus x minus 4 dx. And when I clean this up, I get the integral of 1 to 3 of x squared plus x minus 4 minus x squared plus x plus 4 dx. And if I did everything carefully, I can see that x squared and x squared and 4 cancel. And I actually get the integral of 1 to 3, which is 2x dx. Look at that, really cleaned up for us. So this is going to be, well, that's the antiderivative is x squared, evaluated from 3 to 1. So I get 3 squared minus 1 squared is 9 minus 1. I get that this total area of this shaded region is equal to 8, which is really the same as a 2 by 4 rectangle. Well, you can see the difference between the x's is 2. It'd be like the height was 4. So again, the area of the shaded region, I'm going to do the upper curve minus the lower curve. And I can see on the graph where the beginning and the end for the integral should be. I get that. But I should really make sure they are, just in case I didn't draw something correctly or there's really no grid. So to see where they intersect, I set the two functions equal to each other. I bring the 2x over. I factor out a negative 2. And I get, when I factor it out completely, my two solutions for x are negative 1 and 2. I can see here x equals negative 1 and x equals 2 is where they intersect. So now when I set up my integral, it is going to be the integral from negative 1 to 2, upper curve, which is the f, negative 2x squared plus 4x plus 4, minus the lower curve g dx, which is equal to the integral of negative 1 to 2 of negative 2x squared plus 2x plus 4 dx. And now we just do our antiderivative that we know, negative 2/3 x cubed plus x squared plus 4x evaluated from negative 1 to 2. So you can see the rest of the problem after I took its antiderivative here in red. I had to plug in my numbers, my upper and my lower numbers of 2 and negative 1, and that's here in purple. Some cleanup in orange, and then finally I do all the arithmetic. You know, you got calculators, you can just plug things along. I like fractions, do not give me decimals. It actually turns out to be nice. The area is equal to 9. Same size as a 3 by 3 square, if you think about it. The difference is x's is 3, and the rest is 3 by 3 square. It's pretty amazing. Okay, for this next problem, I have to find the area of the shaded region. It's actually regions. I have two shaded regions that's stuck between these curves because these curves overlap a few times, creating this two shaded regions. Yes, I know I can see on the picture where they do intersect, but I actually want to figure out algebraically. So I set them equal to each other, bring over what I have to. I decide to factor out by a half x. I get x squared minus 6x plus 8. And I factor that. Let me change colors just because so it stands out. I get a half x minus 2, x minus 4 is equal to 0. So I get three solutions for x. 1/2 x is 0. I also get 2. And I also get 4 as the points where I intersect. So you can see right here at 0, 2, and 4, they're intersecting. So what does that mean? I'm going to be setting up two different integrals. I'm going to set up one integral going from 0 to 2, and when I do this integral, the top curve is the f, and the bottom curve, or the lower curve, is the g. And then when I go from this second integral that goes from 2 to 4, this time the top curve is g minus the lower curve of f. So to find the shaded region, it's going to be the integral from 0 to 2 of f, 1/2 x cubed minus 2x squared minus x squared minus 4x dx plus, now the integral of 2 to 4 the other way around, x squared minus 4x minus 1/3 x cubed minus 2x squared dx. Let's see, parentheses. There we go. Now when I clean this up, I'm going to get 0 to 2, and it's going to be 1/2 x cubed minus 3x squared plus 4x dx plus the integral from 2 to 4. And when I do it this way, since it's backwards or the other way, it's going to be exactly the opposite. Negative 1/2 x cubed plus 3x squared minus 4x dx. When you subtract in reverse order, you get opposite results. So when I take its antiderivative, well, x to the third is going to be x to the fourth. I have to have a 1/8 up front, minus x cubed plus 2x squared evaluated from 0 to 2, plus, now I'm going to get exactly the opposite of what I had here, negative 1/8 x to the fourth plus x cubed minus 2x squared, but now my limits are 2 to 4. Okay, so after I set up my two integrals for each sliver, from 0 to 2 for the first and from 2 to 4 for the second, I plugged in my upper and lower limits for each. I did a whole lot of arithmetic. I wrote it all out. You could use your calculators and do this and that, but the total area is equal to 4. In fact, both little areas, both little slivers have area equal to 2. Both of them are exactly the same size. Even though they don't look the same shape, they have the same size. Okay, thank you for watching this video.